I seem a little uptight today. It's because we just bought a new house this morning, and anyone that's done that before knows you're basically running on adrenaline at this point. It's a lot of exciting things going on. Anyway, I want to talk to you today about our work on navigation and robot teams. Basically, a lot of the work we do is team-based, so a lot of those issues, certainly a lot of issues at the single vehicle level that we address as well, but we've also been thinking about it at the sort of multi-vehicle level. I mentioned the uncertain environments in part because we're thinking not just about worlds in which we've either pre-mapped, and so you'll often hear people talking about things like Waymo go out and actually map the world and then drive around in that world. We're thinking about things that are sort of partially known and to the point of not known. Give a sense of the different kinds of things we do. These are actually applications I'm not going to say too much more about, but they'll give you a sense of the different things that we do. One of them has to do with a giant lab that we actually have. We were fortunate to build on campus, actually, and it's basically this one right here. This is actually just half of the lab. These quadrants are actually flying around. They're actually hexes doing formation flying, using sort of relative navigation as a mechanism to figure out where they are. The floor looks a little bit weird, but it's intentionally dirty. They're actually using the markings on the ground as part of the localization. If it looks like star maps, it's sort of the kind of are, but they actually have cameras on them looking down and using that to do navigation. So this is sort of, this is the formation they're actually trying to form. So you get into issues here of navigation, communication between the robots themselves, how they actually share landmarks and actually work together to do that navigation problem. The other type of work, and actually I'll show this video a little bit later, but it's sort of working in a robot driving through an environment which isn't just complicated in a static sense, but also has people in it. So this is Building 32, the data center over here. We were driving around back and forth for a bunch of times. And collision avoidance in this case is relatively straightforward. I mean, sort of simply hitting somebody is not the objective. What we actually wanted to do was to demonstrate we could behave in a socially acceptable manner. So we're actually driving in ways that would be sort of, the people would appreciate as being an acceptable way to behave as a robot. So we'll talk about that a little bit later. Over here, we actually have robots, and again, you can actually see the two halves of the lab I was describing over here. This is the left and that's the right. They're actually working together. This is actually a multi-robot learning problem. They're actually learning how to push these gray balls. Those don't exist in real life, but they're actually sort of pushing them in simulation, and the simulation is running in parallel with the real life. But they're actually learning how to work together. They're actually doing transfer learning, so they learn from each other. They also learn how to exchange information. So the blue agents and the red agents here now are actually learning how to transfer knowledge from each other and actually sort of exchange that knowledge. This is difficult to see somewhat intentionally. This is my old lab, which was pretty crummy. What's happening here is that oftentimes you'll see labs, you go in, you see the lab, there's robots flying around. It's kind of interesting, somewhat like this picture. But for the vehicles that actually have cameras themselves, it's kind of boring to look at. There's not a whole lot going on in that environment. So one of the things, the challenges we have is how to make it interesting. Now you can make things interesting by going outside, but if you've flown outside, that's just hard and complicated and takes an awful lot of time, and you can't do things at 4 in the morning. So what we had actually is projectors in the ceiling. They exist in this lab, but we weren't using them here. So we actually have projectors in the ceiling, essentially projecting a movie onto the floor, which we then can create through simulation. In this particular case now, the vehicles are flying around, and again, you can't really see them in this video, but they're up here about 3 or 4 feet off the ground. What you can see with these inset pictures is actually what they can see. They're looking down at the ground, and now they're actually looking at that ground. Essentially, it's a movie. We've got little clouds flying by to create some occlusions, and they're now actually collaborating together to perform essentially a delivery task. And so they're flying to places, picking things up, and moving them to other places. So these are the kinds of sort of coordination activities we're doing. It includes the sort of path planning, the tasking, the perception problems of am I actually seeing the right thing, and how do I actually know where to deliver it. One of the other problems we've been thinking about is, of course, more delivery. Everybody's interested in delivery robots. And so the ubiquitous robotic movie for delivery is I have a moving platform and I come and demonstrate I can fly over and land on a moving platform. My challenge to the student was to make something that's a little more interesting than that. So what we actually have on here is 2 leaf blowers. And we actually have a howling wind of about 7 meters per second over the landing platform. So we can't drive at 7 meters per second in this lab. What we could do is drive at about 1 meter per second and create a wind of about 7 or 8 meters per second. So we're actually now demonstrating that we can come over land and so we can acquire the target. It's on the back of the landing vehicle here, acquire it, and then land on the vehicle even at the high relative speeds of the wind. And so that's basically what's happening here. The last thing I'll just mention here is that we, we do, like I say up here, there's an awful lot of work on vehicles driving around trying to make sure that we are avoiding humans in this particular case. And this is a situation where this is a bunch of sleepy grad students at about 3 in the morning making the, it's the last day of the videos are due for the robotics conference, and the student doing the work has rustled everybody out of their desks and said, walk around and don't be like a zombie. I'm not sure if we've succeeded in that because it looks like a bunch of zombies, but this is thinking about the specifics of how to make sure we can do collision avoidance. And that's sort of a classic demo we'd run in the lab where you sort of bring people in and of course everybody tries to break it by jumping in front of the robot. Anyway, so what I'm going to do is just it gives you some highlights of the types of work that we do. My lab's experimental. Use the experiments to motivate the kinds of questions you're asking. Then you go off and answer the questions, and you come back and do experimentation work afterwards, sort of demonstrating that you've addressed the problem, you're getting sort of good, half-decent results out of it. But at a high level, the kinds of questions that we deal with in the terms of multi-robot autonomy have to do with the sort of a partial list here. And one of them has to do with navigating. So it's sort of how do we move around quickly in the types of environments. And again, I say unknown. Typically, we'll work in a domain where we might know where we are, but we really have no idea where anything else is. And in particular, like I said, in the moving robot case, we might have a sense of what's right around us, but we don't have a bigger sense of what's going on the larger scale. So of course here you want safety, you want tractability because we're going relatively quickly. You want to make sure that this thing can be computed fast. Other kinds of questions, whenever you're doing learning, and what comes up is how do you certify anything? How do you know this is actually going to work? So it's a big question having to do with the learning techniques. So we'll talk a little bit about our attempts to address those questions. One of the questions that has to do with a lot with the exploration, the delivery robots, is just how well do you actually know the environment you're doing delivery? And so one of the questions we're looking at here, it has to do with contextual or semantic relationships between objects, and how those are used to actually help us plan well beyond our actual knowledge. And the point being that semantic labels actually give you insights on how things might be connected in the world, and you can take advantage of that in a planning framework. So we'll get to that in a second. The last thing has to do with the classic question I have for any time you're doing multi-robot stuff, is just to what extent do they actually agree in the language they're actually using to communicate? And if you've probably experienced this on the phone where you end up, we're talking to someone you maybe not met before and you realize you're having a whole conversation, then you were misusing the same words and you actually agreed on something, but you actually had a different meaning of what those words meant. It happens all the time with humans, and it certainly can happen with robots. And we'll get to an example of the type of issues we have here. The bottom line is that what you'd like to be able to do is just share information between the robots. They have different partial views of the world. You'd like to be able to fuse them, but before you can do the fusing, you have to make sure there's an alignment process. It essentially ends up like a big permutation. I just need to make sure that we are in agreement before we fuse on that we're actually talking about the same thing. Once that alignment is done, then we can do a fusion. You'll see a lot of people talking about fusion. You'll see thousands of papers about these algorithms called consensus. They've already presupposed an alignment vector. They've already dictated ahead of time what that alignment was. And once you've done that, you can just fuse away. In the real world, you don't know what that vector is going to be. And that's the question we're trying to address. So it's align first, fuse second. But again, this has to be fast. And so again, a lot of this has to do with just how quickly you can actually do this process. All right, who's in charge of time? Because I'll just talk forever. So that clock says 10 past 2, and we're ending at 35, right? Yeah. Cool. So fast and safe planning, and again, this is a really redacted set of slides, so I'm going to hesitate to even say we're going a lot of depth here. I'm going to show some videos, talk about concepts. Any questions that come up, just let me know. Most of these have links like this, so you can get from GitHub with the paper themselves. A lot of these papers are in archive. This is actually just presented at IROS in, wherever that was, last week. Possibly Japan. It may have been Korea. I'm not sure where the students went. So here, we're interested in, again, the classic problem of can you fly quickly in a not particularly well-known environment? You might have had a map of what it looked like before an event happened, but then maybe an event happened, and now you don't have a really good sense of what you're going to be flying into. So for a bunch of different sort of operational reasons, we'd like to be able to do this quickly, but of course we want to make sure we're doing it safe. And if safety requires you slow down, then you slow down. But if you're able to speed up and go quickly, you should be able to. And so the classic problem that you have here is the world sort of ends up looking like, there's a known piece, a piece that might be, in the sense that Well, there's going to be sort of occupied known, free known, and then unknown. And I'll talk about the colors in a second. But the blue here, the cyan, ends up being the sort of the unknown piece. The orange ends up being the occupied known, and white in these pictures are effectively the known free. In the classic difficulties, what I'd like to be able to do is to plan a path. And I'm at A, I'm trying to go to E, and I'd like to be able to just plan a path from A to E and optimize with some cost function like time and just get there as quickly as I can. If you just assume the world is known, you just plan a path, this red thing, and just say, I'm just going to plan that path and be really optimistic about what's going to happen. Of course, the problem is there may be something out there you don't know about, which is this sort of unknown blob up here, which is on that path. And of course, I show it as being here, but it could have been like right here, right at the boundary between known and unknown. And again, keep in mind, we have limited field of view sensors. We don't know what's out there. We're flying about 3 or 4 or 5 meters per second. We can only see about 3 or 4 meters in front of us. So we're going to get surprised a lot, okay? So we're going to be flying along, optimizing for time along this red trajectory, and all of a sudden, sort of right at that boundary between known and unknown, something appears, and the robot throws his hands up in the air and says, don't know what to do. You need to have a backup plan, right? So one backup plan is you just don't do that, right? You just stay in the known space. You just sort of puddle along like this, and you get to E, and you hope everything's great. By this point, the horizon recedes, and you just keep going slowly like that. So you got the optimistic but completely unrealistic, safe but super slow, and this basically ends up just being sort of fast and unsafe, okay? So the gap then is how do you actually sort of get the fast and safe trajectories? And ideally what we're going to end up doing and what we actually end up doing is creating sort of 2 paths, the red, which is optimized under the optimistic assumptions, but at the same time, we have a deviation point R, which is then at what point we basically decide to bail and actually go to a backup plan, which is this sort of path RF, which is our safety plan. Now, what we actually publish is ARF. We publish this. We go from here to here to here. We say, that's it. And if you don't hear from me again, that's what you follow, right? And the planner then obviously is recalculating this as quickly as it can. But you're running an online optimization. If you run optimizations like this, you actually don't know if they're going to end. It's a stochastic end time. So one of the failure modes is this: the next time you run this optimization, it simply doesn't finish in time, because this is a clock cycle. We're churning around as fast as we can. And if your optimization ran and didn't succeed, that's considered a failure. Another failure is that there's a big obstacle sitting right here that we knew nothing about, and our red line's plowing right through it. And we get hugely surprised, throw our hands up in the air, we see it, but it's just jam on the brakes, and it's like, now what, right? And the point being, you need to know this information about this point, at which point you can bail and leave, right? And that's basically what we're doing. Now, the trick is that, this is computationally difficult, and what I've just done is sign us up for not just one computationally difficult problem, and now doing 2. Because I need to solve the red path and solve the green path. And the question is, how do you do all this and actually get it done in time? And that's really what the trick was, to actually figure out how to do it efficiently and how to get efficient heuristics, which is what this graph ends up looking like. I'll get to this picture in a second. It's right here. So if you've seen these types of optimizations before, you'll recognize a lot of this junk. This is a massive mixed integer quadratic program you run. It's massive in the sense that there are lots and lots of variables, but it's really short, right? In the sense that it's not looking that far into the future. So it isn't that hard to actually solve. But there's a big challenge that shows up, is that this is all done in discrete time, which is essentially picking these green dots. But these green dots are, the blue dots. The blue dots are actually described as a location in space, but you're still missing the notion of time. And so what you actually do is separate the optimization out. One is the space optimization, the other is the time optimization. You separate the 2 out for simplicity, okay? But then you have to do a second step that says, okay, I've agreed to go through these blue dots, but now I have to decide how long it's going to take me to get to each one of these blue dots. And that's the real question. What my student Jesus was able to figure out was that basically you can do essentially a line search. So the first calculation to find the blue dots is actually pretty straightforward. We can do that really fast. The calculation to figure out how to distribute time along those blue dots is actually pretty complicated. But you can imagine that if I try to get between those blue dots really fast, you end up zigzagging all over the place, and the vehicle might saturate its actuators and not work particularly well. You go too slowly, you're probably not optimizing the performance that well. So we actually do a line search, and basically what happens is, say, time instant k here, you might search and choose a particular value and realize it fails, choose another value, it fails, another value fails, and then you find one that works, and we're just basically searching along here looking to see what types of values might work for time distribution. The cool thing is that each one of these is actually really fast. Each of these is only about 4 milliseconds, and we can do a bunch of these, and then there'd be a total of only about 15 millisecond calculation. which gets us to a fast enough cycle time for the entire system that we can actually run all these optimizations in real time. And actually, so this is all running on board the vehicle. We actually are flying with an i7, a Nook on board doing these calculations. So we run all this optimization and run that line search. And the total amount of time for this is, like I say, about 15 milliseconds. So you pull up some tests and you start doing the ubiquitous forest. This is sort of a standard benchmark problem for this type of work. You download a bunch of other optimizers and see how they're doing. And again, we're sort of running both of them. One is doing about 15 milliseconds, the other is about 20. So we're designing both parts of this graph in about 35 milliseconds. Again, fast enough for what we're doing here. You compare it, this is us down here, FASTER, cool acronym. You compare it with all the others, and in this particular case, we're just comparing distance traveled and success rate, and for all the others, we're able to download and run their code against this application domain. Oops, what happened there? Wrong button, go back. Okay, now we're going the wrong way, go back. We were as successful as others. Of course, this was actually us as well. This is our previous work, and this is the next work. So the best competitor to our current work was our previous work, but we were still better than all the others in this case. So this is the kind of thing you would see when you're flying. This is working on, this is sort of a bunch of different images showing you the world. We're actually flying around in an office environment, which have a lot of what we call bug traps, right? You fly into an office, you can't get out of it, you need to turn around and come back out. And that's actually what it did just there, which is actually, and what it's creating here is a very localized map of the world. It doesn't have a big map because the representation scale is complicated here. If you make a big map, it's hard to update it. It takes a lot of time to do that. So it keeps a little map of about sort of, in this case, about 10 meters around here. Each one of these are voxels, right? And so it sees stuff, it fills that occupancy grid in, says, I've seen some stuff, but basically it's keeping that little local map around it. And as it flies along, it basically just throws that map away. Now, we throw it away and put it in a big map, but we're not updating that big map in real time. This map is actually used for part of our planning. And what's described in the paper, if you take a look at it, is the way we're actually doing these calculations quickly is everything gets broken up into these polygons, and those are those green polygons those blue dots had to fit in, and that's sort of the way that we actually do the calculation really fast. So the result is we can do that pretty quickly, and we're actually able to fly that. So now we actually go into my lab, and the first set of experiments are just running through about half of the lab, sort of flying it up over stuff. And again, it's in these examples, it's the same as I described before. The vehicle knows where it is. We're using motion capture to navigate it, but it has no idea what else is in the room. So now it's just zooming back and forth in the room. And this is where it's using the sort of RealSense, the vision system to look ahead as a point cloud, so it gets a sense of what's in front of it. It gets surprised by some stuff and then sort of goes around it. And it's particularly jumpy here because we've really tuned the attitude to high performance. So it's very sort of agile in its ability. So it'll do like Millennium Falcon type maneuvers if necessary to fly around things, okay? You get a sense of sort of the velocity profile up here, which we're also optimizing as it needs to, okay? All right. So this is path planning, and like I say, it's one of the things that is nice about this, and in fact, if you compare it against other algorithms, this is just a plot of sort of velocity versus distance. Not only are the paths we're creating shorter than other people's paths, we're actually flying faster along those paths than other people are as well. So it turns out to be a very effective technique. And so you get reductions in both flight time and also distance. And like I said, the hardware experiments actually got up to about 7.8 meters per second in unknown environments, which when you don't know what's in the room is pretty fast to be flying. Because again, we can only see about 5 or 6 meters in front of us. And so it's pretty shocking when you see something at that speed. Okay. So changing gears a little bit, that's what we're doing in terms of flying when we have sort of limited perception capability for airplanes. This is the work we're doing when we have limited perception capability for ground robots. I mentioned this and we've sort of seen this video, but I'll play it here. It's sort of, so a lot of this work started off with the interest in being able to fly, or drive in this case, through environments with pedestrians. It's just sitting, getting prepared, ready to go. So we have a fairly high level sort of planning scheme for avoiding the obstacles. What it's now focused on is the moving people. And again, part of the challenge here is being able to predict where these people are going to go, the extent to which they're going to cooperate with you or not. And so there's a very challenging planning or sort of aspect of the planning is that prediction and knowledge of sort of what else is going to happen in the world. And so in a lot of these cases, we have to make sort of educated guesses as to the extent to which these objects are going to be in the way at some point in the future. And the scalability of the algorithm in handling that type of prediction forwards can be quite complicated. So that's how Mike, the student working on this, sort of that was his master's thesis. One of the questions he then asked was, typically we're going to drop a robot off at the end of a driveway. We're doing a delivery. It might come off the car, it gets dropped off, and then you have comments like, go, deliver this package to the door, which makes perfect sense to a human. Doesn't make a whole lot of sense to a robot. It's missing basic things like, where's the door? What does the door look like? What is the map of this world? Now again, you could go through and map every environment you're going to go to, but the notion is this is any house in any neighborhood, and you just say, deliver this. So one of his questions he was looking at was there a mechanism by which he could use the knowledge that he is able to get from the robot to find a faster way to get to the door? So what he's taking advantage of here is the fact that we already know how to do a bunch of different things. And I think Luca Carlone is going to talk later, and he's an expert on things having to do with SLAM. So these techniques exist. We already know how to do planning algorithms over here, but one of the things we were missing was an ability to start mapping together the things that we do know, right? Like we're measuring things, we have a geometric understanding of the world, but we can also start developing a partial semantic map of the world. And by that, what I mean is things like, this is a stage, this is a floor, the door is over there. And so you can start labeling things at the semantic level. Then you can start understanding the relationships between semantic things, like if you're in an office, there tends to be tables and chairs, so if you see tables and chairs, it's likely that you're in an office. And if you're in an office, it's also likely you might start seeing a printer. So you can start making semantic relationships like that, at that level, which you can then use in the planning process. So what he's thinking about here is, for instance, can I start linking together things like driveways, sidewalks, hedges, bushes, and things like that as a connection mechanism to figure out where the door might be relative to where I am. But again, you're able to make connections that go way beyond the physical distance you can see because you can now start thinking about things at the semantic level. Now, anytime you have sort of one map that looks like this ends up being an image, which is sort of my semantic understanding of the world, at least at some partial level. What I want at the planner is something that's going to end up looking like a cost to go. If you've done things that look like receding horizon control, you know you need to have some sense of how do I get to where I'm going. He needs to connect these two things together, and that ends up being a giant mapping problem from one picture to another, and that's, of course, another deep learning problem. And so that's actually the technique he's been using to do that. He went through and hand-labeled a whole bunch of satellite images to get these semantic maps, then created the end result, masked them all up, and then did a giant learning problem to get a policy from this that actually enabled him to do that. The results are shown qualitatively here. And the fact that you can't tell the difference between these two columns is a good thing, because that actually means it's working extremely well. And this paper was also presented at IROS last week, so it's available on arXiv if you want to take a look at it. But the fact of the matter is that it's working extremely well for what it is we're asking it to do. And so if you compare that with, I don't know why this is skipping two. If you compare this with the standard thing you might expect to do, which is just exploration-based planning, where you're just saying, I'll just drop the robot off and let it explore, you can do that, but it's going to be super slow. And what he's looking at here is different types of environments and how his algorithm works compared to the exploration technique, and the result is pretty good. So he's been doing this in Unity, so we're doing sort of simulation-based training, but in the past week or so, he's actually been out in Michigan working on doing this on real robots, and I think, I'm not sure if we're actually going to have time to watch the whole movie, but basically what he's showing here in this picture is the process of I dropped it off, it saw the linkages, and what he ended up making up here is that partial semantic map, the estimated cost to go. He uses the cost to go to then educate his planner, and his planner then decides where to go. And so it's a little bit jerky, just because of the way the simulation runs, but this is sort of what you would expect the robot to be doing, hopefully a little bit smoother in the way that it actually moves. And so this is sort of what we hope to demonstrate in the next couple of weeks. And so Mike's actually beginning to think about future directions for his thesis work. One of the things that's come up is sort of anytime, again, you're doing deep learning, there's a question of, how is this going to work, or will it work? And so one of the questions here is a classic sort of issue in terms of anytime, like I say, you do neural nets, there's lots of examples that have been created where people put little things down, and it then convinces the algorithm to go and do stupid stuff like drive on the other side of the road and crash into people. And so the question that we had was whether or not it's possible to achieve some type of robustness in the deep neural net that we're actually developing, either for the type of work that Mike's doing for the delivery robots or just in general for the other kind of learning work. And so classically, the picture that we have is this, that basically we're a robot down here, the red guy, we're trying to get to our goal up here. So it's like a collision avoidance problem. There's just an adversary sitting in the middle here who not only can take an action to sort of defeat us, but actually can fool us ahead of time and deceive us by creating like an illusion of what it is that it's doing, which we then respond to as a red guy and then sort of try to go around him, and then the blue guy just sort of leaps over here and then ends up being in the wrong place. And the result is that we end up crashing into them. So what we have to do is what's captured in here, which is basically we need to come up with an action which is sort of essentially a measure over the set of actions we can take of the worst possible thing that can happen. And this is, if that's all, that's the problem statement, that doesn't really solve the problem, it just writes down what the problem is. It turns out if you take a standard sort of sampling-based strategy to figure out what is the worst case possible thing that could happen, this is very, very difficult to compute and very, very hard to do. The good news for us is that there's a bunch of people in the computer vision community been doing a similar type of adversarial problem, but they're worried about things like dogs and cats, not collision avoidance. It's like, can I show you a dog and convince you it's a cat? What we're interested in is whether or not I could have a blue agent or an adversary show me one thing and then fool me into doing a maneuver, which then I end up crashing. And they came up with a great way of actually doing a lower bound estimate of essentially what this thing is in this yellow box here, which is exactly what we need to know. And it's very fast, and we can actually run this in real time. And what we get out of this is not just a measure of this is what we recommend you do as a policy, right? Because we've designed a policy that's going to recommend you do something. We can actually analyze in real time how confident we are of the success of that. Like how safe do we think that policy is? And so we haven't necessarily sort of guaranteed it will be safe, but what we will tell you at execution time is whether or not we think it's safe. And so you can then use that to decide whether or not you're even going to execute it. And the result is, a picture somewhat like this. We're depending on how much robustness we embed into our uncertainty and what the adversary will do, we basically can dramatically lower the probability of collisions in this sort of simplified problem, the collision avoidance problem we've got. Okay? So that's pretty cool, because this is now taking applications or techniques that have previously only been used in very simple problems compared to what we're looking at here, and then advance them into a prediction over time of whether or not a collision might actually happen, which is a much more complicated problem than people had done before. And this paper was presented at Coral, which was 2 weeks ago, and this was the one that was in Japan. So there's a paper online if you're interested in reading about that. Okay? All right. So the last piece of work then gets into some of the multi-robot stuff, and it's trying to develop what we call here a consistent multi-view problem. So a classic sort of scenario is I have a bunch of cameras that are all looking at this famous rabbit, and the question is how do we actually align all these point clouds so that we can actually begin to fuse? So we need to agree we're all looking at A, the same rabbit, and B, what part of the rabbit we're looking at before we actually make this decision ahead of time. So that's sort of in a nutshell what we're trying to do. The sort of another way of thinking about this is that we go off and see the world and we come back and we're trying to align our different pictures of the things that the landmarks we might have seen. For instance, we might getting confused here about the Stater Center and whether or not it was a landmark, and whether or not it was actually connected to things like the Eiffel Tower and the Statue of Liberty. Okay. Now, again, classically here you'll see people doing pairwise type of alignment. I'll agree with you, you agree with someone else, and we'll just do all this in pairs. This is sort of the classic solution. What is completely missing, though, is the ability to use redundancy, because if we can all come to a consistent agreement on what's going on, now we have many, many people agreeing that redundancy, just like any other noise reduction problem, allows us to get some type of the sort of a noise reduction in sort of the actual sort of alignment aspect of the problem. So now in this context, what that ends up looking like is the word cycle consistency. And in this picture, what it means is these green triangles. We basically want all of these things to agree that this is the Eiffel Tower. And once we've done that, now we can start reducing the amount of noise that's in this alignment problem that we actually have, okay? Now what you'd like to be able to do is to do this fast, and you'd like to be able to do it with high precision. And there's a bunch of techniques out there, some of which are the graph-based models, which are fast but not particularly high precision. The convex approaches or convex relaxations are high precision but not particularly fast. Spectral graph techniques are over here. Our technique actually shows up about here. Now this is a cartoon, I'll admit. I'll show you some data in a second that actually sort of confirms that that's roughly where we end up. But we gain the benefits of a lot of the convex relaxation and spectral graph techniques. And we basically just combine the benefits of these two to get a much better technique. And this is actually just one data set we were looking at. This is our algorithm here, clear. And again, this is on the precision versus time plot. Basically, it's 1 over its sort of frequency. So you want to be over on this side. You want to be on the top corner. So it's similar to this graph here, the spectral methods on this plot. But if you actually skip to the next one that's looking at both precision and recall, the spectral technique actually got really good precision up here by having really crummy recall, and is down here. And so our technique is the only one that's sitting up here. And so this is now allowing us to do consistent alignment between these groups of vehicles at a very high speed compared to some of the others. And so to give you a sense of that time scale, we've actually flown this on robots. This is actually flying around at NASA Langley. The picture here, and in fact, I don't think I fully appreciated why people keep getting lost in forests, is that trees turn out to be really useless landmarks. They're just big round things. They all look the same. And so for a robot flying around, it's very difficult to figure out how one tree differs from another. The point being that the geometric layout of these trees actually is the true signal that you need to look at. Difficult for us to see, easy for robots to see. What they're actually doing is working in pairs. They never actually meet each other, but they actually see things in common, and at this point realize that these two maps that we're making separately can now be aligned and cojoined because they've actually seen the alignment between these two sets of features. And once they've done that, of course, they can now actually create one giant map, which is the two maps actually fused together, which is, again, a little bit difficult to see with the perception, but you get a sense of the, like with the video here, but you get a sense of the intent. To get a picture of how this works, this is sort of us, one of the robots flying around making a map. This is what it's supposed to look like. This is us. This is some of the other algorithms that exist that have been published. All these red lines are bad answers. So this is sort of the baseline, lots and lots of bad answers. There's connections being made between things that make no sense whatsoever. Some of the algorithms are able to get rid of them, some not. We get rid of most. This is our, before we do anything, this is us. We have some red lines left. But basically, there's just not a whole lot of data here. So we've made connections between things, and there's no real data to suggest that we made any errors that just don't have enough data. You can actually, they're just outliers. You can trim them out. When you do that, you, of course, get the result that's sitting here, which is almost perfect. So from a performance perspective, we look great. What's super great, though, is that in terms of runtime, we're orders of magnitude faster than some of the others that are good in terms of performance, but pretty crummy in terms of computation. So. We're sort of, as shown in the previous plots, way off in the top right corner compared to some of the others. It's starting to look pretty good. Anyway, I think out of time, so I'll sort of stop there. Like I said, there's a ton of work we do in the group. Some of the videos on the front sort of showed things that we've not even had a chance to talk about today. But they sort of have a lot to do with navigation mapping, single vehicle, multi-vehicle. A lot of other work we do also has to do with things like information sharing. How do you even decide how to share, what to share with other people? And when you share it, how do you even use it? We do a lot of distributed optimization for these multi-vehicle work. But a lot of the things I've talked about today sort of applied to sort of will illustrate the work working in uncertain and unknown environments and how to get computationally efficient techniques in most of these domains. Again, we're somewhat vehicle agnostic, as you can tell. We work with air, ground. I actually do work underwater. I used to do work in space. You give me a vehicle, as long as it moves, I'm interested in it. And with that, I'll stop. Thank you.
Great. So if you have a couple questions, I will pass the mic around, and then I want there's a stand if you want to line up too. So, sure. Are there any questions? Here's one.
Yeah, so I just noticed that it looks like you're doing everything passively. Do you do any work like active sensors?
You mean like laser?
Yeah, like LiDAR or something, yeah.
Yeah, it wasn't obvious, but the video, this vehicle flying is actually navigating using a laser. So there's like a planar laser that's on it. And so what it's actually doing is mapping, so you can kind of see, like in the range that it's getting here, it sort of sees a lot of trees. So this flies with a laser. The robot that was moving around on the ground, the socially aware thing, that had a giant Velodyne on top that we're actually using for truth. So we actually use vision-based cameras with a LiDAR for navigating. And then but often, like when you go back and take a look at the video, it's like, well, what happened? So we actually drive around with the Velodyne on top, and that collects all the truth data, which we can then post-process, and then sort of see what's going on. So So we use a lot of active things as well. I mean, it's right.
Okay.
And it turns out that the quadrotor that's flying through the space, that has a binocular camera on it, like a stereo pair.
Right.
But it's actually a active, because it's actually pinging at like the 950 nanometer IR range. So it's basically sending out a pulse, and so it's an active light beacon.
Okay, interesting.
Any other questions?
So this demo is done by 2 drones, or it can be scaled up to many drones? Or what's the
So
minimum information they share, or what kind of advantage when you share
Yep.
that? Yeah.
So in this particular case, and again, it's a little bit difficult to see in this video, it's easy to see on the screen, but on the computer. So they're actually, again, making an independent map, which is then being brought, and the maps sort of look like this, right? At the scale of a single vehicle. And what they're doing is navigating and sort of determining where they are and where all the things are around them. But they're doing these separately. This is being shared with a local, with the hub. And on the hub, you're then running the alignment algorithm, saying, oh, these two things actually seeing similar things. Now, ideally, that'd be running on the actual onboard vehicle, but it's difficult to get this software running on that vehicle, as it turns out. What's happening right now is each vehicle is broadcasting to a place. We're running the algorithm, seeing the alignment, fusing the maps, and then once the maps are fused, they're then being republished out to the vehicles as, here's the new map. And again, once you're able to fuse, you can now get much better accuracy because you're now able to use landmarks that the other vehicle had already seen, right?
I was thinking about formation flying through that kind of area.
Well, I mean, they are, so in this particular application, they're actually trying to stay away from each other. They're trying to explore that world, and so there's no real incentive to be close. But when they are close, they'd like to take advantage of the fact that the point being, I can use features that you saw, even though I haven't seen them, and if you knew where they were, then that helps me navigate because I now know where I am because you're basically telling me where those things are, okay? And so that's essentially what happens.